simply just talk about what's the next step after this project. Okay. I know most of you guys are expert in the inertial confinement fusion experiment, but I want to simply introduce what is the inertial confinement fusion is, because my parents are still here. So, what is the inertial confinement fusion? It just use high laser power beams to shoot fusion fuels, and the laser beams will compress the fusion fuel and induce the continued fusion ignition or burn process. And for our target structure is most important in this process because it's the position to store the fusion fuels. This is one example for the target structures. It's combined the two parts. The first part is called capsule part. It's a shell to store the fusion fuels. And then another part is the fuel tube. It's just like its name, it will fuel the fusion fuel into the capsule. And it also supports the target structure in the center of the target chamber when they do the experiment. Before the laser fusion experiment, the target structure was covered by thermal surround. When they started to do the laser shoot, they will remove the thermal surround, and the laser beams were uniformly covered on the surface of the capsule to cause the continuous fusion burn. And during this process, they have two challenges. The first one, the fuel tube of the targets must limit it to the 10 micrometers diameter for near the capsule part. Means at this area, the fuel tube diameter should be limited in the 10 micrometers. And for the target, and another challenge is that the target must become stationary within the 150 milliseconds after the thermal surround is removed. And this removing process can cause a large vibration for this target structure. So I will detailedly introduce the challenges. The first challenge is why we need smaller fuel tube for the target structures. At first, from the experiments, the NIF finds the targets with the 2 micrometers fuel tube performance much better than the 5 micrometer fuel tubes. And for our omega target, we want to use a 10 micrometers diameter fuel tube to replace the 30 micrometers diameter fuel tubes. There are two reasons to cause it. The first one, the mass. The mass attached on the capsule can cause the Rayleigh-Taylor instability, and this Rayleigh-Taylor instability is the main reason to cause the fuel to produce continuous fusion burn or ignition. So which means less mass on the capsule, more chance to cause the fusion process. So less smaller fuel tube means less mass. Another reason is that the smaller fuel tube can be easily figured out from this picture. When they do the laser fusion experiment, the capsule is fully covered by the laser beams, but it still has some fuel tube will block the laser beams. So the smaller fuel tube means less laser beams will be blocked, and so more uniformity of the laser drive will be covered on the capsules. So after the first challenge, we know we need smaller fuel tube structures. This causes the second challenge more serious, because this target structure is fragile and unstable. It's because it has a big head, very thin neck, so it's very easy to vibrate it, very easy to shake when you vibrate it. From the experiment, they take some image from the General Atomics. They find during the inertial confinement fusion experiment, white noise, they have a large displacement and a shape change. And I also simulate this process. And we find this my simulation result is perfectly match the experiment result. And from the simulation result, we can figure out it had during the vibration, it causes a large displacement and a large shape change for the target structures. And this can cause some problems. The first one, the large displacement and the shape change can increase the can cause damage to the fuel tube and capsules. From the simulation, we can figure out there are a lot of stress on the fuel tube during the vibrations. So which means that the fuel tube can break at any time during the vibration. And that's at room temperature. If in the cryogenic temperature, the stress will become larger. So the target structure at the cryogenic temperature is harder to survive. And so improve the survivability of the target at room temperature, cryogenic temperature is our first requirement. And the second problem is that more than 5 micrometers displacement is unacceptable during the laser fusion experiment. You can see during the inertial confinement fusion experiment, all the laser beams are fixed. When they do the laser fuse process, so the laser focal area is fixed. When the capsule has more than 5 micrometers displacement, they are out of range of the focus point. So it will decrease the uniformity of the laser beams covered on the capsules. That's our requirements. We need to limit the target structure into the position, limited our target structure into the 5 micrometer displacement during the fusion experiment. Okay, how could we solve these problems? There are very simple ways to solve it. We can use a passive isolation to dissipate energies from the target structures. A good example for the passive isolation is the car's shock absorber. When you drive a cars on the road, there are a lot of things can generate vibrations. The engine, the road will cause a lot of vibrations. But the car shock absorber dissipate energies from these vibrations, so it limits the vibration transmitted to the car's bodies. So we want to develop a foam structure to around the fuel tube to act as a passive isolation. And this foam structure will not only dissipate energies, but also will have a low density as possible and as smaller as possible. Meanwhile, this foam structure should have a minimum mass contact with the capsule and should not block the laser beams when they do the laser fusion test. There are 3 critical things can control properties of the foam structures. The first thing is identify the foam materials. The second one is unit cell shapes. The last thing is the density of the foam structures. Depending on these 3 critical factors, we plan to have 5 steps for our project. The first one, we will design the structure in the certain areas. The certain area is 1 cubic millimeter, and then we will use the calculation to determine the structure's load and strain values. And the third part is most important part. We will use manufacturing of these structures and demonstrate the size and the resolution achievable. And after we got the physical sample, we will test these structures' mechanical performance at room temperature and cryogenic temperatures. Then we will choose the best performance of these structures. After we choose the best performance of structures, we will determine the best energy dissipation performance. The energy dissipation performance for these structures. Okay. After we have the plan, we figure out the manufacturing method is most important things in this project. So we decided to use a 3D printer as our manufacturing method. Because 3D printer could create a microstructure with a sub-micro feature size in a very easy way. And also 3D printer can print a lot of the foam structure under the same printer setup, and this structure can have a consistent performance. And the most important thing is that the 3D printer could allow us to use the polymer as our material, because the polymer has several advantages. The first one is it has a high viscoelastic properties. The second advantage is that the polymer has the ability to print a small size with precious structures. The third thing is important thing is that the polymer has a high potential for some viscoelasticity at the cryogenic temperatures. Okay, what kind of 3D printer could print out these tiny structures? We use a two-photon polymerization 3D printer. It's like a traditional laser 3D printer to use a laser to cool liquid resin. At the focus point, the liquid monomer will transfer to the solid polymer. But two-photon polymerization 3D printer has a very high resolution compared to the traditional one. That's because it had a smaller focus point. From this picture, it shows that this is a traditional laser 3D printer. In the large area, there's the focal spot. It's a large light point. And for our two-photon polymerization 3D printer, it's only in the center dot. Yeah, same as a white dot. Is the focal spot, which means this 3D printer has very high resolutions. So our 3D printer resolution could achieve 500 nanometers. So it fully meets our requirements to print out micro-sized unit cells. And this is the print process. It's print by layer, and each layer is less than 1 cubic micrometers. Depending on this high resolution 3D printer, we can print out a lot of same structures on the same print setup. Okay. After we have toys, we need to decide what kind of unit cell we want to print out. We use we use that structure as our unit cells because they have a very novel behavior. They cause a negative Poisson ratio behavior. For the conventional structure, it just have a positive Poisson ratio behavior. Just when you compress a form structure in another direction, you will have expanded, right, with the normal structures. But for our Z structures, when you compress in one direction, in another direction, you have a shrinkage. Because this novel behavior, we can figure out this structure has a high resistance and a high energy dissipation abilities in the mesoscales. This is a compression process for this for the audacious structure. For the audacious structure, it compresses the form structures and gets a stress strain curve. Because we will use the similar experiment process, so I want to simply introduce how the stress strain curve works. At first, this form structure is a linear elasticity. It's from the plot 1, it's a straight line. And from the straight line, we can get the elastic modulus for the form structures. And after point 2, it's zero stress, the form structure achieves the plateau absorption area. If the form structure wants to absorb more energy, which means that this form structure could absorb more, the more strain should be at the plateau absorption areas. And until the form structure will achieve the densification part, which means that this form is crushed. Okay, when we have the unit cell, we have toys, we definitely need to print out something, that's right. There are 3 form structure we print out. Well, first one is the 1 cubic millimeter. Another 2 is the half cubic millimeter. And here is the example for our form structure, if you guys can look around. And for 1 cubic meter forms, you can see it can be for our first two picture. You can see these two structures are very similar to each other. That's correct. They have same structures, but they don't have same scales. And our third form structure, we can call this as our first generation form. And the third form structures is derived from the first generation form. I decrease the thickness of the unit cell, and so the form density decreased. Is our second generation form. And here is two examples. This one is 1 cubic meter forms, and this one is only half cubic meter forms. So it's hard to say, but and meanwhile, we also print out solid things to use to measure the materials properties. Okay. There are two ways to measure the materials properties. The first method is called the three-banding method, and the second one is called nano-indentation. The three-point banding, we just place our solid beams on the support, and in the center, a probe will be compressed. The equipment will record the force and displacement curve, and depending on this curve, we can calculate out the Young's modulus of these materials. And for the nano-indentation, there is a tips will compress on the material surface. They have two parts. One is the loading force part. Another part is unloading force part. And depending on the unloading force process, the equipment will calculate out the nano-indentation. From these two methods, we find these two results is quite similar to our literature results. The reason we want to measure the materials properties compared to the literature value is because we want to make sure our print setup is correct and the resin is fully polymerization. Another reason we want to measure the materials properties that because we don't have the literature value for at cryogenic temperatures. So I use the three-pointing banding test to measure out the Young's modulus at cryogenic temperatures. And all these values will be used to calculate the form structure and also will be used in the simulation. And for the form structures, we use the crush compression test. At first, we use a 1 cubic millimeter form structure to do the compression test. We applied 1,000 millinewton force on the top of the surface. And this is the maximum force for the equipment. But we didn't see the negative Poisson ratio behavior. Yeah, we compressed, we didn't see obvious shrinkage in the vertical direction, and we didn't crush these structures. The first form structure is just like our preliminary test. So it helped me to improve the experiment process. Because during the compression test, we figured out we compressed the form structure several times, but we find at the first cycle, it have a low values in the rest of the values. We think this may be the gap, maybe the gaps between the equipment and the samples cause these low values. So during the rest of our experiment, we will run the compression test several times and then ignore the first values. After the preliminary test, we will I shrinkage the form structure to the half cubic millimeters. This time we break the form with 500 millinewton force, but we still don't have obvious negative Poisson ratio behaviors. They still have shrinkage in vertical directions, and we find this structure is very brittle. It breaks at 3% strain. As what I talked about, if you want the form structure to absorb more energy, you want more strain at the plateau absorption area. And we also want this structure to become more elasticity. So one easy way is just to decrease the thickness of the unit cell. Also, use the simulation, I figured out as a corner, at the edge corner, hold a lot of stress. So I also enhanced these areas to develop our second generation form. Okay, after we enhance the corner of the edge and decrease the thickness of the unit cell, we develop our second generation form and do the test. After we decrease the thickness, the elastic modulus definitely decreased a lot, and the yield stress decreased, but the strain at the field increased 500%, and the total energy absorbed before the foam break increased 100%. That's a very remarkable result. That means our foam structure, the second generation foam structure, absorbed more energies than the first generation forms. And during the compression for the second generation foam structures, we observed the shrinkage at vertically, which means this foam structure has obvious negative point concentration behaviors. When we apply the 170 milliNewton force on the top, they have a 4% strain at the lateral direction and have 5% shrinkage at the vertical directions. And our simulation also proved this result. So from simulation, they have a similar same displacement, and also the simulation can give us some details for this structure. These details we cannot know from the experiment, just like a stress. From this picture, you can see this unit cell in the red area hold a lot of stress, and in the blue area, this part don't hold any stress. So if we want to develop a new structure in the future, the red area will be enhanced, and the blue area can be decrease the thickness. Okay. Just what I said, we not just use the experiment results we just also use the simulation and calculation result to prove our experiment results. From the simulation, we use the finite elementary analysis as our method to simulate the compression process. At first, I want to simply introduce what is the simulation process. At first, we use the 3D design software to design the form structures. Then we export a file. This file will be used in 3D printer and also can be used in the simulation. So the physical sample should have the same structure with the simulation structures. During the simulation, I have the same process with the compression, apply the force on the top of surface, and record the displacement. And depending on the force and displacement, I calculate out the elastic modulus of the foam structure. And for the calculation is depending on this equation. And this equation is calculates the unit cells the structure and calculate out the whole structure's elastic modulus. Depending on the unit cell thickness and the length and the angles between the force and the edge, we can calculate the whole four structures elastic modulus. Compare these results, you can see they are perfectly match each other, especially for our second generation foam structures. And it proves that these results are 40-degree convergence. Depending on this 40-degree convergence results, I also use the simulation to simulate another auxiliary structures, and we figured out our auxiliary structures have and get the plot between for our auxiliary structures, and this plot is the relative modulus and the relative densities. The relative modulus is the ratio between the form elastic modulus, and the structure's Young's modulus, and for the relative density is the form density is the ratio between the form density and the solid densities. there should be have some relationships for the traditional random structures. But for our this curve is for the traditional random structures, and this curve is for our auxiliary structures. They have a higher values than the traditional random structures. That's because I think our auxiliary structure is orderly structures. So the area base is fully loaded when compressed, which means the mode density is loaded stress when during the compression. Because of this reason, I think the related modules should have some relationship with the thickness and length. So I got the plot. If I will find out, this is linear relationship between these two values. So which means in the future we want to design these orderly structures. We just change the thickness and the length for the loaded bins. Okay. After we design out the better generation foam structure in the crusher test, we will test this foam structure on the repeating peg test. This repeating peg test is just like we apply some function force on the foam structures. So this foam structure will apply some function string, and I will measure out the shift between those two strings. And from this shift, we can calculate out the loss energies from the foam structures. And we figured out at the room temperature, this foam structure loss energy achieved 97%. And even at the cryogenic temperature, the loss energy still have 94%, which means the most energy was dissipated during the compression. That's a very good result for a foam structure to dissipate energies. Depending on this, we want to use this foam structure to assemble on our target structure to dissipate energies. But we need to figure out where is the best position to locate our foam structures. At first, we use a high-speed camera to record the vibration process. It's a shaking from experiment, it's from the General Atomics, and I also use the SS simulation to simulate the vibration process. You can see these two images perfectly match each other. And the data is very similar to each other too. Depending on this plot, we figured out this area is the best position to locate our foam structure. The first reason is that in these areas, the foam structure don't have a contact with the capsule. The second reason is that in this area, the foam structure will not block laser beams during laser experiments. The last reason is in this area, the fuel tube still have a large displacement. So during inner vibration, the foam structure still can contact with the fuel tube to dissipate energy. So after we figure out the best location, we will assemble this structure together. Okay, there are 4 parts for our assembled structures. The first one is the fuel tube. The second part is the support structure. The reason we design this support is because we don't want to glue the foam structure directly on the fuel tube. If we directly glue a foam structure on the fuel tube, it will bending with the fuel tube, so it doesn't have contact with the fuel tube. So we glue one side of the support on the base of the fuel tube and glue another side with the foam structures. And the last part is the capsule part. And the capsule will glued with the 10 micrometers displacement tips. And this capsule will be coated with aluminum because it will be used in our next vibration test. And after we assemble these structures, we have an SEM image. We find that the fuel tube is in the center of the foam structures, and it doesn't contact with any of the foam structures in the static states. Okay, we are not just use the empty target structure as our control group. we also use a solid structure as our contribute. The solid structure is only different with the foam structure is that we use a solid part to replace the foam part. And this solid part has same mass with the foam structures. The reason I want to use the solid part, that's because we want to exclude the materials influence. We want to make sure, these structures dissipate energies, not the materials to dissipate energies. After we have these samples, we will test this structure under the free vibration test. And that's the most important part for this project. There are two things combined in this setup. The first part we will call the vibration source. This part is called the laser detector. When we start finding the vibration source, then we use a lot of time because we try to use a hammer to shake the field tube. We try to use a moving stage to shake the field tube, but it's hard to control. But finally, we find a very easy way to control the vibration. Use a speaker from the audio. And this speaker will be controlled by the function generator. This function generator will control the frequency and amplitude for the speakers. So when I started to do the experiment, the target structure will glued on the speaker. And this is the capsule, and in the dot is our foam structure on the solid structures. And the laser detector will in this area and will record the displacement and time for this target structures. And from the laser detector, we can get a displacement time curve. And from this time curve, we can get a decay curve. Compare this damping process and the decay curve, we can measure out this foam structure is dissipate energy or not. Okay, when we do the vibration test, at first we just use the low frequency to vibrate the target structures. We vibrate the target structure as 7 Hertz, but as a 10 voltage amplitude. So the target will start shaking at 80 micrometers displacement. But after 50 milliseconds, the field tube with the foam structure, the displacement was limited to the half micrometers. And the field tube without foam structure still have the 2 or 3 micrometers displacement, which means the foam structure definitely dissipates some energies and limits the field tube at a low frequency. So in the low frequency, the foam structure works. How about the high frequency one? We tested all the samples at a very high frequency. The high frequency is each sample's natural frequency, because at the natural frequency, each target will have a large displacement. At first, we compare the decay time. When the target decay to 40 micrometers, is 94% of the total displacement. The field tube with the foam structure just use the 0.3 seconds, and the field tube without foam structure still use the 0.6 seconds and 0.7 seconds. That's a 50% decreasement. That's a very good result. And if we compare the decay curve, the red curve is for the decay curve for the field tube with the foam structure. And the green curve is the field tube with the solid structures, and in the center, the yellow one is the field tube, no foam, no solid, just the target structures. We find that at the bottom is the field tube with the foam structures. It have a significant decrement. And our exponential values also prove that. This result means this material didn't dissipate energies, but these foam structures definitely dissipate a lot of energies. and help the target structure stabilize more repeatedly than the filter without form structures. Okay, for the future work, we want to do the damping in the cryogenic temperature. But there have two challenges for that. One is how could we create a cryogenic temperature for the target structures. Another thing is how could we record the vibration during the cryogenic temperatures. So I figured out these systems can solve these problems because these systems have the cooling system. This cooling system uses a helium and vacuum to create low pressure to create a cryogenic temperature environment. And use a high-speed camera here to record the vibration process. And from the image from the camera, we can get the damping displacement and the time curve. Okay, another future work we want to use a new resin to manufacture our foam structure. The new resin have a very high elasticity, so it can hold more force and can have high energy hold high energy dissipation abilities. But there are the problems to print out these foam structures. If we use the original recipe to print these structures, you have a series of shrinkage problems. But at first, when you set up the new recipe for the new resins, then we can add some support structure for the new resins for the foam structures. This will help to our new structure, how our structure with the new resins become more uniform. Okay. Conclusion is that for my project, we demonstrate the negative Poisson ratio behavior for our foam structures, and we measure the elastic modulus for the material and for the foam structures at room temperature and cryogenic temperatures. And we also compare the experimental result with our literature value and prediction values. And figured out we have a very similar result. And for our crash impact test, we develop new generation forms and find it can absorb more energies at room temperature and cryogenic temperature. And for the repeat impact test, with the new generation form could dissipate a lot of energies at room temperature and cryogenic temperature. Then we figured out the best position to locate our foam structure. It has large displacement and avoids the laser beams. The last step, when we assemble the foam structure into our target structures, we do the vibration test to test it. It has a very significant result to show that our foam structure definitely can improve the target survivability and stability in the inertial confinement fusion experiment. Okay, let's see the acknowledgement. First, I need to thank you, Professor Harding, as my advisor. I think I'm lucky to be a student. He's very professional and very kind, and he used a lot of time on me. And thank you, my committee members, Professor Asmati, Professor Poisson, and Professor Lambert-Proust. Thank you for your time. And I need to thank you, my collaborators, the target groups. And without your help, I cannot finish my project. They are very high professional and high technology colleagues. As what I said, if I said, who can make American great again? These guys.
Carefully. You're saying I agree or disagree with you.
It's a joke. And finally, I want to thank you, all my friends. You guys are making my boring life become more colorful. Yeah, and finally, I want to thank my family. Hi, Mom, Dad. I know you don't understand what I'm talking about. I will translate to you when I come home. You boys will come home soon. Yeah, that's all my presentation for today.
Okay, let's open it to the audience. General questions, anyone?
So you were developing all these really high resolution structures, did you have any issues while you were printing with manufacturing? Like, did you see stitching effects? How did you mitigate stitching? Did you see any of those kind of building effects kind of come up in your data analysis when you're doing mechanical testing? It would be very interesting to hear about.
Yeah, actually, yeah, that's a very good question. Actually, I'm proud to say I'm the first guy to use this system to print the foam structures. So there are a lot of things need to be done as the first one to use these systems. Just like you need to choose the right recipes. Just as you said, you need to figure out how to solve the stitching problems. The stitching problems didn't influence me a lot because our structure had I just increased the thickness as this connect part. So that's the reason I increased the thickness at these areas. Another challenge, another problem when I do using these systems, I think I spend a lot of time on how to get used to use it. Is that a question?
Yeah, thank you.
Just like if you want to develop a new resin, it will use several days or several months to figure out the new recipe for the new resin.
What's the print time for one of the structures?
For the foam structures, if you want to print all together, it's 1 hour at first. But when I'm familiar with these systems, it's just to use 15 minutes. Because I set up different print speed.
1.5 minutes? 15?
Yeah, 15.
And was there any post-processing required after it was printed? What kind of post-processing?
Post-processing, what I did is just I want to make sure the resin is fully polymerization. I just use the UV light to cure the all the foam structure.
A general question. You use the word auxetic. Could you tell the audience who may not be familiar with that word what it means? And why did you choose to print a structure with a negative Poisson ratio?
Oh, that's a good question. Auxetic structure, you want to know what the word means or just what is auxetic structure?
Both. I want to define it.
Actually, I googled what is auxetic means. It's from the Greek word. It means it's increased. It also expanded. That's the word means. So which means also for the compression, which also means when you compress, you have a shrinkage. That means the negative Poisson ratio behavior. And the reason I want to use the negative auxetic structure is because we want to make sure this structure is in the centering area, and we don't want this structure to be expanded when you compress. Auxetic structure also meet our requirements. When you compress, it's just shrinkage. It cannot more than this area.
Okay. And one follow-on question, if I may, and then I'm done. Where would you say is the biggest leverage if this project was being continued? Where would you say effort should be spent? If you were to apply this to test an actual target, because you showed some energy dissipation, but is it enough energy dissipation? If you wanted more, what would you do?
More, just what I. From the simulations, we can just depending on the simulations, we can figure out if you want this foam structure to become more elasticity, we need to decrease or increase decrease the thickness or increase the length of the unit cells. And from the stress of the simulation, we need to enhance the red area. Just like this area hold a lot of stress. This part we need in stress. But if we want to decrease the density, we just decrease the thickness of the blue area. That's most important to develop new foam structures depending on the simulation stress plot. And another ways to increase the ability to dissipate energies is just to use the new resins. That's actually we actually want to do in this project. Now for the next step, this PDMS is high elasticity, so we can hold more force and dissipate more energies. If we can print out these foam structures as the same structure.
So of those two, new resin or new design, where do you think is the most leverage, most potential?
In my opinion, is the new resins is have better choice.
Okay, thank you.
Sorry.
Okay, this will be quick. So you have your tube and you have the damping structure, and there's a gap between the two in your experimental setup. Is that correct?
Yep.
There's a small gap between. So in my mind, I'm thinking, as this vibrates, it flows through space and then it impacts the side of the damping structure, and then it begins to compress the damping structure. Is minimizing the gap?
It is possible, because that's the reason we built these support structures. I didn't directly glue the foam structure on the fill tube, because if I directly glue the fill tube, just like you said, it will bending with the fill tube.
It'll influence the fill tube itself. It'll bend. I see.
But if we have
So
this,
you want it as close as possible,
as close as
but
possible,
not
glue.
influencing
Yeah,
the fill tube.
that's correct.
I see.
I can ask you one last question. I mean, we'll go through the exam, but follow up to Professor Harding's question. So this new resin that you said is higher priority from your perspective. So has there been some indication as to its cryogenic temperature properties? Is it?
It's not.
Is it more that have a higher modulus? Is it expected higher modulus? What happens with viscoelasticity? I mean, it's a promising material, stiff at room temperature, but how about cryogenic temperature? Just give me a 2 sentence answer. Is there information in the literature about cryogenic response of the new resin?
No, we don't have the values for the cryogenic temperature. So, and even for these materials we used for my project, they don't have a cryogenic temperature values from cryogenic temperature. So that's the reason I measured out the Young's modules at cryogenic temperature.
I think just to follow up on that, it is PDMS, which is a very soft material, but because it goes through the 2BP process, we don't know how closely it approximates actual chemically synthesized PDMS. So it would be a good test to do.
Hey, Ming, this is Mark Whitman remotely.
Hey, Mark.
Good presentation.
Okay.
Question for you. Do you expect the modulus to change even further below minus 140 C, for example, when you go down to 20 Kelvin where the cryogenic targets are actually shot? And number two, have we tested this on an actual cryo target to see if they reduce the vibration amplitude at shot time? That's all, thanks.
Okay. Sorry, could you repeat your question again? I didn't hear clearly.
Is it because you can't hear me well, or I talk too fast?
You talk fast for me.
All right, okay. So do you expect the modulus to increase as you go lower in temperature to cryogenic targets where solid hydrogen around 20 Kelvin, or do the, say, properties stabilize or saturate at liquid nitrogen temperatures? And number two, has this been tried with actual cryogenic targets to see if there's a reduction in the amplitude at shot time?
Oh, okay.
Questions?
Yeah, I understand. I think I understand. For your questions, I think we didn't. We just tested the cubic samples in the cryogenic temperature, and it shows that it could dissipate energies, but we didn't do the target vibration test at cryogenic temperature. Actually, it's a future work for this project. And for cryogenic temperature, for the cryogenic temperature, for now, what I use is just use the liquid nitrogen to cooling down the systems. So the temperature could just achieve the minus 140 degrees. Does that answer your question?
Yeah, to some degree, you expect it to go through a glass transition temperature, and most likely stabilize in terms of its.
Because our formal structure is polymer, so the glass degrees can be ignored.
Is it not the case for the structure?
Yeah, it's not the case for this structure.
All right. Thank you.
When you were modeling the vibration in your FEA code, what were you using as an input for like the vibrations that you might experience? Was it based on just the video and trying to match that?
Oh, you mean the field target is vibration?
Yeah.
Actually, I just use the I fix the vertical direction. I just have the motivation in the y direction. So then I just measure the nature frequency for each for this target. So you can see. This image, actually, these are two kinds of nature frequency for these target structures.
Okay. So you were measuring the natural frequency
Yeah.
of the star. Okay.
How did the two compare? How did the calculated natural frequency compare with the measured natural frequency?
This is actually sometimes it's lower than the measured frequency. Is a 60 hertz, but when I do the experiment, some field tube do the 60 hertz, but for some experiments it's 80 hertz. I think it's maybe the glues problems. The glues adds the mass, so the densities will change.
Okay. Any more questions?
I mean, the follow-up to that would be, did you measure the diameter of the glass fill tube? Because that stress goes into the fourth power. So if it's even 1 micron, maybe that would change your resonance frequency quite a bit.
You mean measure the
diameter of the fill tube.
for the field tube?
Yeah, it can affect, it can be a strong lever, the diameter of the fill tube, when you do your modeling. In comparison,
we
calculated versus, right?
This is a 10 micrometers.
That's 10 micron.
10 micron.
Okay, and you measure that.
Yeah, measure it. It's very easy to, because you use the 3D design software, it's very easy to measure out.
Okay.
Okay. Well, let's thank our speaker one more time. And I'll hand over to the chair of the defense. For those people who are not part of the